Morning, everyone. Welcome to our second installment of Colloquium 2.0. Colloquium 2.0 is the SVC's newest program that's designed to combine the elements of our Webinar 2.0 series, which is a 1-hour tutorial on a very specific subject, followed by 1 hour of a separate event, which is a roundtable discussion. So a couple rules of the game here. One is we ask you to put any questions you might have in the chat. Try and keep them to a minimum because we like to address the questions in the roundtable discussion. I have the absolute pleasure and honor of introducing Rob Belan and Duane Bingaman, the Kurt J. Lesker Company. Over the years, we've been colleagues, we've been competitors, we've been peers, we've been foes. But at the end of the day, we've been respectful of one another in terms of offering to our customer base solid solutions. And what you will see in this presentation is an agnostic approach towards the fundamental aspects you need to take care of when you're looking at system design. So with no further ado, let me please introduce you to Rob Belan and Duane Bingaman.
Good morning, everybody, and welcome. Today we're going to cover system design. Originally, this is a day-long course. It's been condensed down to a 1-hour kind of presentation here. So, of course, there's going to be a lot of detail missing, and we apologize for that in the beginning. This should encourage you, if you like what we present here today, to investigate the SVC and look at courses that might interest you, and please take them. A very worthwhile organization, and all the educational material that's presented in the SVC is of great help to people in the vacuum industry, thin film industry. So we would recommend that. Duane, you want to say good morning?
Good morning. Yeah. So, okay. Yeah, I'm here just to weigh in occasionally with Rob. Rob's going to do the bulk of the presenting here, but between the two of us, we have a fair amount of experience in this field. So hopefully we can bring forth something you may not have known.
Absolutely. We've worked together. Duane and I have worked together for quite a long time.
Yeah, we don't need to talk about how long. Okay.
We've been through many different scenarios, many different technological challenges, and to date, we've come out pretty successful. So we hope to impart some of that knowledge to you in this presentation on system design. Some of the preliminary disclaimers. The SVC is putting this program on and believes that everything we present is going to be real and not copied from anyone else. They would also like you to know that we as the authors own this presentation, and you are not authorized to replay this unless you have our express permission. So I told you this is a day-long class normally. We're going to try to condense it down to 45 minutes. So here's a brief layout. We're going to put together a purpose and scope, hopefully, of the system or the deposition system that we're trying to make or build or buy. We're going to define the necessary vacuum levels that we're going to run at, or we want to specify our machine operating at. We're going to discuss some of the implications and impacts that the substrate size, quantity, and condition impacts on the system design. We're going to discuss some of the common misses that people tend to overlook when it comes to vacuum systems, deposition systems, when they install them, when they go to use them, some of the common misses there. We're also going to look or talk briefly about budgets and quotes and dealing with vendors and consultants, in trying to achieve the ultimate goal, the ultimate desire, which is a working vacuum system that fulfills its purpose and its plan that you have put together. I'll start by taking a look at what's out there. There are a couple of different approaches. Custom design systems specifically suited to your needs, or adapting your needs to a standard type of system design. In one, you're telling a vendor that this is exactly what I want, and I want you to design something just like this. And the second case, you're saying, hey, you offer a line of systems. I would like to look at a certain model of that line, and I'd like to investigate if my process will fit in that system. So two different approaches. We'll talk about the benefit of either and try to lead you and guide you down a path so that you can make an informed decision when it comes to your system. Now, there are all sorts of vacuum systems out there. There are big ones, there are little tiny ones, there are glove box compatible systems, there are cluster tools. There's huge vacuum systems that people can stand up in and play a game of catch if they want to inside vacuum systems. And there's even bigger still vacuum systems. So the technology is out there to make just about any kind of vacuum system you want. The question is, what's practical within your budget level, within your criteria to achieve the goals that you're laying forth? Likewise, your substrates could be vastly different from anybody else's. Typically, when we talk about vacuum systems and thin film deposition systems, we often talk about wafers, relatively 2D, flat kinds of substrates, but by and large, everything under the sun can be coated in the vacuum system. So they will impact the size, they will impact the geometry and layout of the deposition sources. So keep that in mind. If something is unduly complex in shape, it might take a complex approach in order to coat it. Here you see there's a huge 8-ton mirror. It's an 8-meter diameter mirror that Gemini North coats maybe twice a year inside of a large vacuum system. And this mirror is very large. It's incredibly expensive. It requires a certain amount of attention. Whereas if you're coating something like drill bits or tools, you have specific needs for that for sure. But handling these is going to be a little bit easier than handling one huge, very heavy mirror. So another example of parts that could be arrayed in a vacuum system to coat. It's sometimes very complex. It's sometimes very difficult to expose the substrate into the area that it needs to be coated. These are some of the considerations when you're designing a system. So that's the point. You want to look at a vacuum system from how can it coat your substrate, how can it do what you need to do, and it might start dictating the shape of the vacuum system. Also, there are various substrates as well that people need coated, like rolls of plastic. These systems exist. They're very large systems. They're called reel-to-reel coaters. And of course, a fighter jet canopy is also a candidate for vacuum thin film coating. So you might not even have a substrate in your vacuum system. So it's very diverse. The systems that are out there, they can be tooled or arranged to do just about anything. There's endless possibilities. So where do we start? I want a vacuum system. Where do I start? And my adage is, before you design it or start to specify it, you must define it. And primarily that starts with a purpose and scope statement. Now the purpose is kind of going to be an immovable object. You're trying to really identify why you need this vacuum system. or deposition system. It's to replace like an older piece of equipment that does the following job. Maybe it's being bought to add capacity or capability to an existing group of systems. What is the system needed for? What's its purpose? That purpose should be clear and succinct and definite as possible. I can't overemphasize this enough, because it's going to guide your design theory. It's going to guide your interaction with the vendors that you choose or the co-workers that you choose to enter into this project with. Purpose is something that's kind of immutable, and it should not change. Scope, however, these are items that have to do with your system that can change. So what's the budget for this project? And you say, well, Rob, the budget is the budget. It can't change. Well, I would put forward to you that if what you propose, what you need, might not always align with management budget or what you get as a department for a budget. If you can define, hey, the purpose, and I need these things in my system in order for it to function and do its specific job, then you might have a case to go back to management and say, hey, I need a little increase, or maybe I don't need as much money for this. I don't think anybody has ever said that, though. But also, you need to define the deposition techniques.
Yeah, they haven't said that more than once. Yeah, no, Rob, you're making a great point about the budget. I mean, the budget does need to be realistic. You know, if you're trying to create $500,000 worth of value inside of a $100,000 budget, you have to give up a lot on the top end on the purpose. So, but there are also ways, you know, savvy suppliers and people that know what they're doing can make suggestions on perhaps less expensive ways to do things if you've got to squeeze things into a budget a little bit.
I mean, it's always a good situation when the customers are trying to collaborate with a vendor to produce a system that meets their needs. So this collaborative effort can engage a lot of different people, a lot of different ideas, and you might come up with a system, as Duane's saying, that gives you true value for the price that you'll pay for it. So you need to also define the number of parts per day. And why is that movable? Well, it could be that if you say, hey, Rob, I need to do 100,000 parts a day and there's no way around it, I'm going to tell you, hey, that system is $20 million. You might say, I'm crazy, but you know, depending upon exactly what you need, it might add up to $20 million. So you might need to rethink a different way, maybe that's more cost appropriate to lay out that production quantity. Maybe you do 10 runs of 100 parts a day in 2 different or 3 different machines that are basically doing the same thing. And maybe that's more cost effective than trying to build one grand system to do it all. So that's why that's probably a flexible item. System space and users and materials that are allowed inside the system seem to change daily. It's not unusual for us to deal with one person at a company talking about a project, and then maybe 6 months later, that person has moved on or been promoted out of his current position, and this project's gone over to somebody else. So things like this do change. So purpose should not change, scope or things that can change. Lay it out, lay this overall mission out as clear and as precise as possible. That'll help you, and it'll help a vendor, or it'll help a system builder to understand exactly what you need to accomplish. And it may give you some ideas of how to do this in a lot more economical kind of way. The next point is to understand the level of vacuum you need to operate at. What vacuum range are you going to need your system to reach in order to do what you need to do? So there are several different vacuum ranges, and it's really nebulous as to where these numbers lay, and they can change by a decade or two depending upon who you talk to. But space 10 to the minus 10 and lower in pressure is deep or high UHV kind of vacuum, very high UHV vacuum. 5 times 10 to the minus 8 to 10 to the minus 9 torr, we say is UHV. 5 times 10 to the minus 6 to 5 times 10 to the minus 8 torr is high vacuum. 5 times 10 to the minus 4 up to 10 to the minus 1, we consider rough vacuum. And anything above 10 to the minus 1, we consider Hoover vacuum territory. So nothing is wrong with these ranges. You decide, nobody's going to look at you if you say, hey, I need mine to operate at 5 times 10 to the minus 4, and we're going to try to talk you into 5 times 10 to the minus 8. That's not going to happen. So these are just the pressure ranges you need to work in, but you need to define or decide what works for your process, what works for your piece of equipment, and we can outline reasons why you would choose these levels or why you wouldn't choose these levels. Some of the applications of these various vacuum levels are space simulation, which again takes that very high vacuum range from 10 to the minus 12 to 10 to the minus 8, really. Particle accelerators that operate in about that same range. Surface science operates 10 to the minus 10 to 10 to the minus 8 range. Materials research in about that same range. Thin film production and various thin film research can happen from 10 to the minus 10 all the way up to 1 torr, 2 torr in the case of certain ALD and CVD processes. So why define this vacuum range? Why put so much time and effort to really discover what range I want to work at, what range I want to specify for my vacuum system? And primarily, some of the reasons are that that you define the material of construction. In certain vacuum ranges, you cannot use certain materials, and we'll go over a chart a little bit later that shows this. So in other vacuum ranges, you could use just about any material under the sun if you wanted. It also defines joining techniques and sealing techniques, machining and preparation techniques as well. Can it be O-ring sealed, or do you have to have all metal seals? Can I use movable feed-throughs, or do I need bellows to move everything in and out? What do the weld joints look like? Can I use a braze joint in this vacuum system? Do my chamber walls have to be electropolished or highly polished, or can they be bead blasted? How do I clean these parts as they go into the vacuum system? Go ahead.
Yeah, I'd add to that too. You know, one of the things is it also is going to help to determine your expectations on how you're using a vacuum system. If you've got a system at 10 to the minus 10, 10 to the minus 11 MBE tool, you're pretty well aware that you're going to be baking things before they go into the chamber. You're going to spend up to 2 weeks preparing to get to that vacuum level, you know, so you have to be prepared for that as well, because that's going to define throughput and how you can run your work.
Absolutely. So there's going to have to be thought from that perspective as well, because as Duane says, if you put an awful lot of time and effort into getting down to a certain vacuum range, the last thing you want to do is to vent that chamber up to atmosphere the next day and then spend another 2 or 3 days baking out and pumping to get back to the original pressure. It's just not practical.
Yeah, we've seen that over and over again, you know, with different systems. People will make an E-beam system that they want to be UHV, and they'll have small pocket sizes, and they run out of material after a run. So
yeah, and then they have to vent like you said, and they're going to have to bake and pump again in order to get to that, that base pressure. So in certain ways, you have to think about the practicality of what you're trying to do. Vacuum pumps are also kind of broken down into what vacuum ranges they cover. So you'll have to consider, or your vendor will have to consider, how to adequately pump this chamber into the pressure range that you've chosen. So these are some of the common materials used in many vacuum systems. Stainless steel, 304 and 312 are common. Titanium, Inconel, Haynes alloy, aluminum, OFHC copper, alumina, silicon dioxide, Teflon, Delrin, polyimide, silicone, Viton. You can find, if you take vacuum systems as a whole, you can find many of these materials in many different vacuum systems. What can you use in yours, or what do you want your system made out of? Well, it's defined by the vacuum range. Also, as I said, will you require metal seals or O-ring seals good enough? Compression seals, rotating seals, welding prep techniques. All these go into a vacuum system construction, and which ones you use are really defined by the vacuum range that you choose. Here are some examples of vacuum pumps, and there are a wide variety of them. Some of them I've never seen or never used, things like sorption pumps, but these are more common, roughing pumps, turbo pumps, ion pump, a cryo pump. All of these have their ranges or definitive ranges which they work the best. And it's up to you or your vendor to pick which ones suit the pressure range that you've chosen. This is a little chart I composed, and it just demonstrates that the lower in pressure you go, i.e. the higher up you go on this chart, the less and less materials and pumps you can use to make the system and put in the system. The higher you go in pressure, from HV to low vacuum, the more materials are applicable, and the more techniques of joining and sealing are applicable as well. So this I put there in an effort to tell you that, hey, there has to be a lot more thought, time, and effort put into not only the design and construction of a UHV system, but as you're going to see later on, how you operate it, how you maintain it, how you train people to use it. All these things go into UHV vacuum systems. High vacuum systems, they're a little less labor intense. I say that with a grin, but they're more open. And low vacuum systems, certainly a lot of things are on the table there. I can tell you that Duane and I both travel a lot, and it's almost crazy what we see as far as customer operational procedures, how they treat their vacuum systems, because a lot of people are very vacuum savvy, and they understand that, hey, it's not proper technique to touch parts with bare hands, or cough over a vacuum system, or eat around an open vacuum system. But invariably, I go into maybe 1, 2, 3 places a year, and I'm sure, Duane, you do too, where you see all the common rules of vacuum violated by certain users.
Yeah, I've seen people smoking cigars inside of chambers. So,
Don't doubt it.
That sort of crosses the line. Yeah.
Yeah, I agree. The one rule that I'll say, no matter which pressure range you decide to operate in for your vacuum system or deposition system, the better you treat it, the cleaner you keep it, the more it'll take care of you, the less trouble you'll have with it. So please keep that in mind. So again, the vacuum range defines the rules of use. Who am I going to allow to touch the system? What am I going to allow to be put in the system? What kind of cleaning these parts are going to have to go through before they touch my system? What kind of materials can I use in these systems? The level of training the user has to go through in order to use the system. It's also going to define, as Duane pointed out, maintenance protocols. Because the last thing you want to do is spend 2 or 3 days to pump a chamber down to a base pressure, a low base pressure, and then run your process and be forced to vent that chamber in order to replace material in an E-beam or change a crystal or do any kind of routine maintenance. It's just very impractical to say, hey, I'm going to run my vacuum system for 4 hours, then I want to spend the next 4 days pumping it so that I can run it for another 4 hours. It makes very little sense. And that might be true or needed maybe 1 in a million times, but certainly it's not the rule and it's not very practical. The vacuum range is also going to probably set your price, or should set your budget and dictate operating costs, because, hey, as I explained before, the lower you go in pressure, the lower you go, the more it's going to cost to get there, and the more it's going to cost to maintain, and the more it's going to cost to keep it at that low pressure, and the more you're going to have to train people. So price and budget definitely enter into that vacuum range. And the reason why I say this is because it's really impractical to say, hey, I want a vacuum chamber to go to 10 to the minus 12 torr, but I have a budget of $90,000. Unless you have a very small chamber with nothing in it, that's not very equitable. And what's true to my heart is the thin film work, growth.
I mean, underkill it so they don't get, something's happening with my internet connection here. Yeah, I see it both ways. Some people underkill it. They don't really understand what they need or do enough work, and they don't get a good enough vacuum, and then they're sort of stuck. But also, like you were sort of indicating, some people will come in and believe maybe because they saw something in the literature that they've got to have 10 to the minus 10, but it's not fully equated to what they really need. And that's the overkill side of life. I mean, understanding why you need the vacuum, you talked about this before. I mean, that's important. Why do you need 10 to the minus 10? And I think you hit on it on this next slide as well.
Sure. So again, like I say, my area of interest is in thin film growth. And I know this, that, hey, the lower I go in vacuum, the less I expose my substrate and my film to water vapor contamination. Because in any vacuum system, if it's leak tight, 10 to the minus 6, 10 to the minus 7, 10 to the minus 8 torr, your primary outgassing constituent is going to be water vapor. And a lot of materials react with water vapor. Aluminum reacts with water vapor. I'm sure a lot of people have seen a hazy, whitish kind of appearing aluminum film. And some people have a lot of trouble with this, and they can't figure out, well, Rob, people have been sputtering aluminum for 50 years. Why can't I sputter a nice shiny aluminum film and mine come out white and hazy looking all the time? One reason could be water vapor outgassing, and you're not getting the chamber down to a level low enough in order to get as much water vapor out as you can to produce a pure aluminum film. So at 1 times 10 to the minus 6 torr, which a lot of people consider a low pressure, you have 1 monolayer of water vapor accruing at the substrate every second. And that's a large, heavy water vapor load for the substrate to take in, especially if you're depositing at a relatively slow rate. And likewise, 10 to the minus 7 torr, you get 1 monolayer of water vapor every 10 seconds. And 10 to the minus 8 torr, 1 monolayer every 100 seconds. So people define lower and lower pressures in their vacuum system if they need super pure films. And it's based on this outgassing rate, basically, of water vapor. The purer the film, the lower in pressure you must go. So we've seen that the vacuum range will determine many of the system characteristics. The vacuum range will determine the quality of work being done in the vacuum system, and the vacuum range will determine the complexity and potential cost of the system. Again, the lower in pressure you go, the harder it is to make, the harder it is to maintain, and the harder it is to work with. They say nature abhors the vacuum, and those of us who have been playing in the vacuum industry for many years have fought our battles with this old axiom many times, because all you need is one leak in a system, and all the work stops, and you spend all your days and all your nights trying to find out where that little leak is coming from. So vacuum range is very important when it comes to system design, and it's something that requires a lot of your consideration time. Know what deposition treatment techniques work together well and what don't work together well. And most of this is tied to pressure considerations. I can explain this by, you have many different thin film deposition techniques, and they have their associated base pressure ranges. So for instance, for sputtering's base pressure, 10 to the minus 6 to 10 to the minus torr. The working pressure is somewhere around 10 to the minus 2 to 10 to the minus 4 torr. So it's not practical to assume that I can put sputtering guns in a vacuum system and hook up an ALD section to this and run these at the same pressures. 1 torr to 10 to the minus 4 torr does not work really well with 10 to the minus 2 torr to 10 to the minus 4 torr. So knowing which techniques work well is imperative into laying out a system. And that's not to say that we haven't seen a system that keeps or has magnetron sputtering and ALD working. It's just they're done in separate modules. So you might need a cluster tool if you need certain deposition techniques to work together or in sequence. Also, some of the adjunct equipment that you would put on a vacuum system, like an ion gun or radiant heaters or RF substrate bias, a water-cooled substrate fixture, a lot of the adjunct equipment will have pressure ranges which we consider optimum for them to work at, and there's reasons for that, because they might require special water seals or special electrical feed-throughs or something of that nature. Anytime you put a heater inside a vacuum system, that's going to add heat to your system, and it's going to cause the system to outgas at a higher rate, and you're going to wind up with higher pressures as the heater ranges go up and up in temperature. So you have to be cognizant of that. Understand the impact that each additional piece of equipment you're putting on this vacuum system impacts the vacuum system as a whole, and it'll help. The next huge impact on vacuum system design, deposition system design is substrates, the number, the size, the quantity, the runs per day, the parts in a run per day. I can't overemphasize this enough. Substrate size and number will drive a good deal of the system design, i.e. how big the vacuum system has to have. If you have pipe plates that are 7 inches in diameter and you need to coat 1,000 of these in a run, that system is going to be huge. It's not hard to imagine that. So a huge vacuum system is almost as problematic as a vacuum system that needs to go to a very low pressure. And the reason why I say that is because you have to really put a lot of effort and thought behind how you're going to pump a very large vacuum system. So, define the batches, the number of parts, the size of the parts. It's going to define the vacuum chamber size. It's going to define the pumping requirement as well. So what happens if you have a substrate that's made out of silicon? That generally tends to pump quite easily. Silicon wafer has a very low surface area, especially if it's polished. It can't hold much water vapor, and it's not very big. It's, in essence, a 2D flat piece of material that you're putting in your system, and pumping it is going to be relatively easy. But if you have this three-dimensional crazy substrate that's rather large and it has a very high surface area, it might take forever to pump it down to a base pressure that's going to allow you to run your process on it. So the substrate material as well is going to define how big a pump I need on that chamber in order to adequately pump it. It might also identify some of the pretreatment needed for that substrate, especially if it outgasses a lot. And you need to identify the need for masks and fixturing. Duane, have you ever noticed anybody to fail big time because they didn't carefully consider how to put the parts they're using into the vacuum system?
Yeah, of course. I mean, that's overlooked a lot. The fixturing, and like you're talking about, Rob, with the let's say the makeup of the substrate. You know, we see a lot of substrates that maybe are phenolic resin that, yeah, they require a lot of pretreatment, and yeah, just it needs to be accommodated for. There's things you can do. You can do pre-treatments like you're talking about, so that you don't have to impose the burden upon your process chamber to pump all the bad stuff out of the substrate. You can do it before it gets there if you treat it right. But you know, there are areas, industrial places where, yeah, the substrates they sit in a corner in a high humidity environment for a week before they get into a vacuum system. I mean, that's common with automotive coating. You know, whereas in the semiconductor industry, it's in a nice humidity controlled clean room. Substrates are treated well, but it does need to be entertained and taken into consideration.
I've actually had serious conversations with customers as to, hey, in the winter, I have no trouble pumping my chamber down. In the summer, when it's hot and humid out, I have all sorts of trouble pumping my chamber down to base vacuum. It's quite obvious to us that have been in the vacuum industry for a while why that's occurring. And one of the things that happens is that you haven't really, if this happens to you, you haven't really adequately considered the environment and its effects on your vacuum chamber or the parts going into your vacuum chamber. And as a result, you've undersized the pumps, or maybe you need to put more engineering controls into the area that houses the vacuum system. But you have to consider it. I've also had serious conversations with customers that say, hey, you know, the vacuum system is running well, but I've got 1,000 of these parts coded now. What do I do with them? How do I keep them? How do I store them before I put them in little boxes and move them out and sell them and send them out the door? And it's also an equal question, because you have these nice vacuum coated parts or whatever circuits, or I don't care what you're making inside your vacuum chamber, but they're clean, they're nice when they come out of the vacuum system. You got to keep them clean and nice before you send them out to customers. How do you store those parts once they're coated? That's always a good question to think about before you start running parts, not after you've run the parts and you build up this inventory of 1,000 parts and you're trying to figure out what to do with them after the fact. The last point here, not everything works well together in a reliable fashion. That's true. I mean, Duane, elaborate on that. What do you mean by that?
Trying to fit too many things into one function, like load locking large substrates, heating them to high temperatures, manipulating them with tilt, trying to combine things like heating and cooling into a substrate fixture. Yeah, it's all possible. Nearly anything is possible, but is it repeatable and is it going to be reliable? So setting your expectations and really gaining an understanding of more or less the long-term reliability of how something is going to work is useful. Sometimes I would say it's good if the consultant or the supplier, whoever you're working with, comes back and says, no, that's just not going to work. I've seen a lot of people just sort of sign up carte blanche for stuff that is never going to work more than a few times. And yeah, I mean, you gotta think about that and ask questions of people of how they're going to make things work, multiple things work together. Yeah.
So the more moving parts something has, the more likely it is to fail. And that's,
yeah, and then doing it in a vacuum adds further complication to it as well, right? So
absolutely,
yeah,
absolutely. So another thing that people miss, I guess, when they're considering their substrates is, or sometimes they fail to tell the vendor of interest or the people that are designing their vacuum systems, is that, yeah, you know what, I only want to coat 2 of these, but they're, you know, basically the size of VW cars. So they're not that easy to handle. Or, hey, these are small substrates, but they're made out of tungsten and they weigh 20 pounds a piece. So these are vital pieces of information that you need to convey to whoever's going to design your system, whoever's going to build your system, that, hey, my substrates weigh a ton. And, you know, that impacts how things are moved within the vacuum system. That impacts how they can be handled. That impacts how they can be heated, how they can be cooled. Little tiny things like that that are left out of customer requirements that have us system suppliers kicking ourselves at the end of the order or the end of the build cycle. It can be crazy. I mean, we understand substrates, and when you say substrates to me, I'm thinking silicon wafers because that's what I coat just about every day. But you know, they're everything but just plain simple silicon wafers most of the time.
I guess, Rob, I'd throw it out there that, you know, if you're talking with, call it a more professional outfit, be it a consultant or a supplier or whatever, if they don't ask you those questions, that should set off some red flags. You know, if they're not prying for, tell me more about your substrate. How heavy is it? How big is it? How many do you want to do? What's special? That should raise some red flags that you may be dealing with the wrong person, because if they've been through this more than a couple of times, yeah, these questions are incredibly important. They set the tone for everything.
I can tell you that I've had people send me substrates to coat, and, you know, hey, is it possible? And I can think of one case in particular where a certain plastic was being used and the person couldn't define the plastic. It's proprietary. I can't tell you what's in the plastic. I need you just to coat it with chromium. And every time we try to coat it with chromium, we would get an ugly looking film because the part was outgassing. As soon as it saw a little bit of heat, it started outgassing like a banshee. And there was no way the film could stick to it. And there was no way the person would allow us to heat treat the substrate or bake it out before we put it in the vacuum system. So some things just can't happen. Some things, you know, we can't rewrite the laws of physics or the rules of vacuum science and thin film growth just because you need them. And it requires people that really know the subject in order to tell you that, hey, one thing is not going to work, or this process is not going to work on that particular substrate. It might work on different substrates, or, you know, hey, you're okay. So there's a lot to be said about communicating or talking to people that know what they're talking about when it comes to thin film growth, vacuum systems, things of this nature. So if you're trying to build or trying to specify or design a thin film system, the system for making thin film coatings, you're going to want to specify the coating and the uniformity of the film. If it has any color qualifications, there are about 1,001 different specifications you can tie to just about any thin film. The question is that you have to make sure that you specify what is exactly important to your coating or to your films. And you got to understand that the more qualifications I put on that film, the greater the impact on the system price. As long as you understand that, that's fine. We don't mind trying to meet a lot of these specs, but it costs time, effort, and money. Maybe you don't need to meet all these specs. Maybe, hey, I just need to make sure you throw down good looking aluminum at a relatively good uniformity spec, and that's it. Do you really need a resistivity or sheet resistance spec, or a reflection spec on the film, or critical temperature specs on the film? So question is coming up with your film specifications that exemplify the criticality or the core criticality of what you're trying to make, and not go too overboard so that the vendor or the people trying to do the work for you start escalating the price based on your film requirements. So understand what the film requirements are that you need, and understand or have a talk with your vendor as to how practical these specifications are, and do you really need them?
Yeah, and also you want to make sure that obviously they're signing up to these specifications such that when you receive the equipment, they've proven that they meet what you're paying for, before you pay them, as opposed to after.
That's correct. It's funny though sometimes, Duane, because people put these various specifications on the film performance, and then the system gets to their facility and they try to match these film specs, and they don't have any equipment to measure like a sheet resistance, or they don't have a way to do transmission or reflectivity of the film. The idea is if you're imparting or you're requiring these specs to be hit, make sure you can verify at your facility as well that these specs are still being hit in your vacuum system as you run thin film.
Yeah, you would like independent verification, meaning you control that, because some suppliers, they'll, almost all suppliers can verify it at their factory. But you want to make sure that the tools which are being used to verify things are properly calibrated and, working the way they should be.
Yeah, and I'm going to wonder why you put a GMR, TMR spec in your film if when it gets to your facility, you have no way of measuring it. And I'm going to say, hey, was it really that important if you can't measure it? I mean, you have to put a little bit of thought behind what specs you're going to require the manufacturer or the system vendor to meet to qualify the piece of equipment that you're buying. So some of the things that people miss, things like UL, NERDL, CE, and FPA, machinery directive qualifications. Most of the vendors know generally to ask these questions depending upon a person's location, because if somebody from California comes to you, Duane, and says, hey, I want a vacuum system to do relatively simple thin film work, you're going to realize that probably there's a lot more code and regulatory compliances the system's going to have to go through before it gets installed into their facility.
Yeah, for sure they're going to need earthquake bracing. But yeah, I mean, and even within states, you're going to have different localities are going to have different requirements. I mean, UL sticks out. I mean, some people require UL listing. that can get difficult, especially on custom tools. You know, these are not posters, so you know it gets difficult, it gets pricey, and it will inflate budgets. But you know, it's required by the locality. That's, you know, that's the rules people have to play by.
Yeah, I mean, we've supplied systems to people, and take, for instance, we've supplied an electron beam evaporation system to a customer, and the system sat around for a while because according to the NFPA and certain other laboratory regulations, they could not safely fill the crucible up with more material after they had expended the original material charge in their e-beam system. So it's funny that, hey, now you figure that out. I mean, we've been in the process of talking about the system and building it for 1.5 years, and it gets to your facility, everything goes together well, it's up and running, except, hey, now I've run out of material, I need to refill it, but my safety regulations and code compliances don't allow me to just open the door and pour more material into the e-gun. So these things have to be considered. What are some of the larger dollar items on here? Like how expensive is it if you want to decide that, hey, I need to use hazardous gas, or I need to use silane or arsenine on the system? How expensive is that to retrofit into a system once it's already been done? So these are questions you have to ask yourself. Or, you know, what is the price to pay if, or is there any price to pay if I don't look into the safety requirements for my local state or municipality, and some inspector knocks on my door and all of a sudden wants to see why there's this big piece of equipment moving in and what kind of safety compliance regulations I've chosen to ignore in order to get it up and running. So you've got to look at most of these things, and sadly to say, it's kind of important, and it can cost a lot of money down the road if we don't consider some of these things. Now, I put in something like delivery requirement here as well. And so if you order a vacuum system from company X and we agree on a 6-month delivery time or an 8-month delivery time, and what happens to your production level if we don't meet that delivery? How much is that going to cost you if you don't meet that delivery? So these are things that you have to take into mind. Also, on the other hand, what happens after 6 months? I deliver the system and you're not ready for it, or it has to stay in storage somewhere before you can put it into production. So these are questions you have to ask and plan for. Also, I would point out item number 11, the operational budget, because a lot of people don't consider, hey, I'm going to need replacement materials. I'm going to need maybe a spare set of O-rings, gaskets. I'm going to need parts, consumable parts to replace. They don't consider the operations budget. And sometimes people run out of money and they can't run their vacuum system anymore because they can't afford to buy gold or platinum or whatever they needed in order to keep the system running and producing parts.
Yeah, sometimes that initial investment on some of the precious materials can be more than the tool cost.
Absolutely.
Yeah, you can spend $300,000-$400,000 really quickly on an iridium target and you know, of a larger size, or you know, rhodium, even gold. I mean, 4-inch gold targets, you know, little R&D scale gold targets can be $50,000 to $70,000 a piece. So it's important to try to think about this stuff. You know, now, of course, once you've made that investment, you can reclaim some of that precious metal. So you're not spending the same amount every time, but it's the initial fill up that's going to cost you.
And consider how you're going to maintain the system as well. Number 9, equipment needed for systems maintenance. People will call us up all the time saying, hey, I have deposition shields in my vacuum system and they're dirty. How am I supposed to clean them off? Well, it's a little late in the game to be asking that question. I mean, we're happy to tell you, but it's always good to be to have a plan for this before you buy a system and start putting it into use. I don't think it's going to make your management team too confident in your operational management skills if you save some of these questions for after the fact or after the system is up and running. So overall, we've talked about a few things here, but we said, hey, it's a good idea to have a purpose statement and a scope statement of this system, make it clear and as precise as possible. We've said, hey, choose the base vacuum range that you're going to work at. What's the base pressure of my system going to be, and why is it going to be that way? How do I define the system's performance? How many substrates do I want per day? What constitutes a good film? What constitutes a bad film? What qualifications am I going to put there to make sure that I make good product at the end of the day? And the idea here is, and it's a very important idea, that over specification of a vacuum system might lead to unnecessary costs. So if I choose to operate my vacuum system at a UHV base pressure level, it costs me probably $30,000, $50,000 more to buy that vacuum system. But if I wind up running it at 10 to the minus 6 base pressure every day, day in and day out, then I might have wasted $30,000 to $50,000. But the killer is under specification. That's very hard to recover from. If you under specify, I think you're going to wind up paying easily more than $30,000 or $50,000 to make up for that under specification. Sometimes it's impossible to correct or make allowances for under specification. And I've seen this happen to people before, where basically they buy a vacuum system for a certain purpose and they can't use it for that purpose once it's get installed because it was not specified right. These are the things to think about before you buy a vacuum system, before you install it, before you run it. And we've covered certainly some of the most overlooked things: ongoing tool maintenance and planning budgets for this. Also, one of the things is readiness. Once you have the vacuum system in place, do you have the people trained for this? Do you have enough people to run? Do you have a person to oversee or manage or be the tool owner or tool engineer for this system? So planning people is almost just as important as planning the system itself. So keep that in mind as well. Anything else here, Duane?
Not really. I mean, that hits it. You just, see a lot of people, they get a couple $100,000 piece of equipment and they don't really allocate any maintenance budget. I mean, you wouldn't think of driving your car until the tires fall off. These things do require maintenance, and they require skilled operators and skilled people to take care of them if you want to get the most out of them.
Right. One of my favorite stories, I happened to go on an install job at a very beautiful place in Italy. It was very scenic. The people were all very nice. I arrived at the facility. A system has not arrived, on the other hand. It's stuck in transit.
That's not a bad thing. So you hang out in Italy for a week or two.
Yeah, absolutely. Not a bad thing at all. But the funny thing is after the system did show up, it's on a air ride truck. And the manager of the lab looks at me and says, "Hey, Robert, how do I get the system off the truck?" And it's, that, so again, it's a little late in the game to answer. And fortunately, we were able to come up with good answers and scramble. But the more forethought you put into this, hey, do I need riggers, or do I need a way to move the system from the truck, the loading dock, into my bay or my equipment room? These things absolutely need to be pre-planned. It's not uncommon for us to sell a system to somebody and find out that, hey, the system is too big to fit down the hallway, and we can't get it from the loading dock into the room it needs to be in. And, you know, it has to be partially disassembled in order to make that trip. So preparedness, readiness for a system that you're putting into your lab absolutely makes everything go that much smoother and makes you look like you know what you're doing as someone that's managing this project, and it gives management a good feeling that, hey, you've done your job. As Duane mentioned, you might, if the systems order or the system complexity gets up there, it might be a good idea to contact a consultant. There are a lot of people, especially associated with the Society of Vacuum Coders, that know a lot about vacuum systems, a lot about processes, and maybe, you know, if the venue or the timing is right, consult a person that knows more than you on the subject and get their opinion. My only advice there is consultants need to be managed, and you have to define deliverables, and you have to lay out a contract with the consultants that makes sense for both you and the consultant. Otherwise, it can be a catastrophic headache. Also, early on in the process, when you've conceived of this idea, hey, I want a system that does X and Y processes, and I need to do it at a certain rate or in a certain fashion. It's good to outlay this and get a budgetary quote from a couple of reasonable vendors, because that tells you right away, hey, if the hard pass budget you have, and once you get that budgetary quote back, you can see that, hey, I'm within range, and that's always a good feeling. Or, hey, the budgetary quote is a lot lower than I thought it would be, or a lot higher than I thought it would be. Maybe I need to adjust my equipment parameters based on that. So budgetary quotes are a good way to make introductions with different systems vendors. It's also a good way to feel out what you have envisioned. Is it reasonable, or maybe it's not? And then maybe you can get pertinent suggestions for what works together well, what doesn't work together well. Maybe you can do without a certain piece of equipment, or maybe you can lower your expectations in the vacuum range you want to work at. Professional vendors understand, they're supportive of this budgeting process, and they're most of the people that we know, and we know a lot of people that are our competitors and work within this industry. They're happy to give advice. They're happy to try to make you successful at what you do. I don't think there's a vendor out there that really wants you to fail because you have a job to do, you have a project that you want to see through. And most people are very supportive of that. They want you to succeed. Throwing everything out there, just be aware that deliveries are not what they used to be, because things that you hear about in the news, the global chip shortage, the pandemic that's going on now, and you can see help wanted signs if you drive through just about any town in the States now. People are always looking for workers. So all these things combine to affect deliveries, and unfortunately, deliveries are a lot longer than they used to be. Any comment on that, Duane?
Not really. I mean, no. I mean, yeah, things are a little tight at the moment. Hopefully that eases over time.
Yeah, absolutely. We thank you for your attention. If you had any questions, this is our contact information. Please don't hesitate. Thank you, and take care.
Thank you.
Rob and Duane, let me thank you very much for an outstanding presentation. I've been in this business my entire professional career, and I was actually taking notes. So thank you very,
Awesome.
very much. Again, this to all of our viewers, this is a 1 hour condensation of a much larger, in-depth approach to the topic that is offered at our TechCon. So if this was intriguing to you, just imagine what an 8-hour deep dive would do. So I encourage everyone to come join us next May in Long Beach. It does not look like we have any questions, so people have decided to wait until the roundtable discussion. So with that, we'll close out the presentation.